In this fifth lecture of special relativity, we studied the problem of classical collisions, making use of the conservation of linear momentum and conservation of, or variation of kinetic energy. The previous lecture on collision explained how to predict the results of a collision between two identical particles. Here, we will consider the general case of collision between point-like particles that might have different masses. In order to get an insight into the problem, we make use of Newton's third law, stating that the forces between two objects exist always in equal magnitude and opposite direction. Newton's third law can be thus used to solve the collision problem between two particles, as evaluating the force of each particle exerts on the other. By writing the force acting on each particle as the variation of its velocity before and after the collision, and using Newton's third law, we were able to demonstrate that the total linear momentum of the system is conserved during the collision. We then discussed about the classification of collisions, that is, how to distinguish between elastic, inelastic, and completely inelastic collisions. It is convenient to perform this classification in the particular inertial frame moving together with the center of mass of the system. In order to do so, we first revised the definition of center of mass as the weighted average of the particles' positions in a system weighted according to their respective masses. An example of calculation of center of mass was given. Note, in this case, that the center of mass computed in the chosen frame is a function of time, that is, it is not steady. One may wish to compute the center of mass velocity, which results by simple differentiation with respect to time as the arithmetic average of the linear momenta divided by the total mass of the system. Note that if the total linear momentum is zero, then the center of mass is steady. Finally, we gave the classification of different types of collision by measuring the possible loss of kinetic energy after the collision, measured with respect to the frame where the center of mass is steady. This loss is measured by the coefficient of restitution E, which is 1 if the collision is elastic, that is, the final kinetic energy is equal to the initial kinetic energy, between 0 and 1, not included, if the collision is inelastic, and identically 0 if the collision is completely inelastic.